So, we will examine this question. This is the question which is at the top of the slide, is h cross over m multiplied by delta k square into t much less than 1, and this will obviously depend on the conditions of the experiments. So, because the time that you are talking about is this time from the target to the detector. So, that will depend on how much distance is traversed from the target to the detector, means you double the distance and the time doubles, and it is on the left hand side of this inequality. So, we have to be careful about it, and we really need to consider the actual conditions of the experiment. And if you consider a typical collision experiment which is being done in a laboratory, put those conditions in, what is d, it is about 100 centimeters and so on. So, these are very realistic numbers which you consider for a laboratory setup on quantum collisions. And if you put all these conditions, you discover, put in the numbers, do the arithmetic which is just multiplication and division, you find that yes, the answer to the question that you have raised is in fact yes, and therefore you are good. You can continue with your approximation. The higher order terms can be ignored, and you can now write these functions without those dots, without those additional terms. You can write the corresponding wave function, wave packet, for not just the one which is impinging on the target head on, but also at a slight impact parameter b, and then r must be replaced by r minus b, because it is like shift of origin. So, it is r minus b, which is what we have written in the last equation at the bottom. So, here you can see that this is a very simple manipulation of the terms, but it makes our analysis very easy. You can always multiply by 1, which is multiply by 1 phase factor divided by the same and so on. Okay. And by doing these manipulations, you can write the wave function for an incident wave packet which is displaced from the axis of symmetry, and you can pull out all the constants which do not depend on k. If they depend on a specific value of k, which is ki, then they can be pulled out of the integration symbol. They come as multipliers, which is what we have done. And what you see is that you have got a phase over here, and this is a very remarkable result. So, here between these two terms you have nothing but a phase, there is nothing else, just a phase multiplying this integral. There is a constant outside over here which you can keep track of, which is 1 over 2 pi 3 by 2, you can keep track of that. But essentially you have this phase multiplying this function which I have written in the blue, this integral, which I represent by the symbol chi. What is remarkable about this is that in chi, k is integrated out. It is some sort of a shape function, it tells you what is the overall shape of the wave packet, and it is multiplied only by a phase factor, which means that this shape function chi is also normalized, because it cannot change the magnitude in any way. It is only multiplied by a phase factor, and when you take a probability density coming out of it, you can multiply it by a phase factor, and this is what you get. So, 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 you will have just an e to the I theta which multiplies e to the minus I theta which goes to unity. So, it makes no contribution to the overall probability density, and the shape function is normalized and it really determines the shape of the wave packet. So, this is the shape function. It is square integrable, and now we are going to discuss the complete solution to the scattering problem, which is the incident wave packet at an impact parameter b, which we have obtained an explicit expression for, plus the scattered part. So, we have worked with similar expressions when we consider scattering of monochromatic waves by a target, and that is typically what we do in the first course on quantum collisions in quantum mechanics. This is a similar relation, except that this is more powerful, more general. It considers a superposition of waves which is which represents a more realistic situation. So, this is your complete solution, and we know that the phenomenological solution to the scattering problem is that there is an incident wave and a scattered wave, and I mentioned at the beginning of today's class that in a picture you write these spherical waves which are coming out from the scattering region, but it is not isotropic, it is not exactly the same in all directions. There is an angle dependence, and that angle dependence is contained in the scattering amplitude f. The 1 over r takes care of the fact that as the wave packet expands, it is going to go through various spherical surfaces, mathematical surfaces whose area increases as the square of the distance. 4 pi r square is a surface area of a sphere, and since you are not generating or destroying any flux in between, the amplitude itself must compensate for that. So, there is a 1 over r. So, f omega divided by r, the division by r is only geometric, there is nothing, no physics in it. The physics is in the scattering amplitude, which is f, which is the scattering amplitude, which depends not only on k but on the angle omega. So, this is the unit vector omega, which corresponds to the polar angles theta and phi of the spherical polar coordinate system. The theta is the axis along which you have an incident beam, because that is the one which defines a direction, and of course, you have azimuthal symmetry, so many things drop out which depend on phi, but in general the scattering amplitude depends on this theta and phi, and then you have this kr minus omega t is the phase of this term. So, kr minus omega t is the phase. So, when is this phase constant? When kr minus omega t is equal to 0 or is a constant, not 0. It does not have to be 0, but it has to be a constant, which means that its differential must be 0, and that differential will be 0 when dr by dt will be omega over k, which will be a positive number. So, r must increase with time. So, these are spherically outgoing waves. So, these are spherical outgoing waves, and this is your complete solution to the scattering problem. And now, as one would expect, the scattering term vanishes in distant past, because there is no scattering in distant past when there was no interaction. That is when ak peaks around a specific number, okay, So, all is good with reference to this, and now you have the phase which the scattering amplitude, which is a complex number, and I write it in terms of amplitude and phase. Just like you write any complex number in terms of amplitude and phase, I write this scattering amplitude, which is a complex scattering amplitude. And now the phase over here, which I have represented by lambda, you sometimes run out of symbols because there are so many different phases that you have to use, and then if you use different symbols, then what is worse is that you forget which one is what. So, one has to do this analysis carefully, and I hope there are no typo errors in this, but if you detect any, please let me know. This lambda plays a very important role, and you really have to study this very carefully. It is going to be one of the central things in our discussion. So, this is the phase lambda that we are now talking about. It is a phase part of the scattering amplitude. I have written the complete solution in terms of this phase, and this lambda again I expand around a particular value of the incident momentum, because there is a dominant incident momentum after all, about which we can make these expansions. So, I expand this lambda about that ki, look at the first order terms, which is the projection of the gradient along a difference vector. That is the terms which should be added in the first order, and that is important. So, this gradient term, this is d lambda by dk. So, it is divided by momentum, momentum dimension goes in the denominator, what comes in the numerator, the dimension that comes in the numerator is distance. Okay. So, I represent this gradient of lambda by a distance which is rho, and I have this rho dot displacement vector. Okay. This is the beautiful result. This is the gradient in the momentum space, mind you, which is what gave us the distance in the numerator. And essentially, if you look at this relation, you have the component of the gradient along a unit vector over here, and this component of a gradient is nothing but a directional derivative. Okay, if you have an arbitrary function, a scalar function, you take its gradient, so it means that it has got a value which changes from point to point and possibly in every direction, but in which direction does it change most rapidly? That is the steepest descent, and that is given by the directional derivative. So, here you have this directional derivative which is the distance, and this divided by the velocity, which we have studied earlier already, will give you a measure of time, which is the delay. This is the time delay of the scattered particle. The scattered particle, the scattered wave packet does not reach the detector at a time if there were no scattering, but it is delayed a little bit. It is hung up in the reaction zone, and how much is that delay is provided by what we have just determined by this ratio. This is called as the scattering time delay, or the Wigner time delay, or the Eisenbud time delay, because Eisenbud was Wigner's student who studied this first. I think Eisenbud's work was in the late 40s, 1948 or something was his PhD thesis. Then Wigner wrote another very extensive paper on this in the 50s, in the mid 50s. So, this is usually referred to as the Wigner time delay or the Eisenbud-Wigner time delay, and this is coming from the directional derivative of the phase with respect to k. So, this is the directional derivative of the phase with respect to k, this is the time delay, and this is derivative with respect to momentum. K, you can get it with reference to not just k, but with respect to p. P is h cross k. So, you can multiply and divide by h cross, and you can also get it with reference to the energy, because E energy is just p square by 2m. So, if you take this derivative with respect to energy instead of momentum, you will get a factor of 2, because E is p square by 2m. So, this time delay turns out to be twice, you see where the factor of 2 is coming from, twice the energy derivative of the phase shift delta. This is the Wigner time delay. Okay. It is also called as the Eisenbud-Wigner time delay, because Eisenbud was the first one to study it in his PhD thesis. He was a student of Eugene Wigner, and it is also referred to as the EWS time delay. S stands for Smith, who wrote a paper a little bit later in 1960, and I will discuss Smith's contribution, which is very important. So, Smith also arrived at an expression for the scattering time delay, but from a totally different consideration, and I will be discussing this in the next lecture. But it turns out to be exactly the same as the Eisenbud-Wigner time delay, although he begins with a consideration which is totally different from that which was employed by Eisenbud and Wigner. Smith's time delay is exactly the same as the Eisenbud-Wigner time delay, which is what I am going to show in the lecture after lunch, and it is therefore referred to as the Eisenbud-Wigner-Smith EWS time delay, or sometimes as WES time delay, because Wigner is the most important contributor to this whole physics. But I think in the literature most of the references are as EWS time delay, which is more or less the time the terminology that we have now adopted, although in some of our earlier works we might have used WES, but it is the same thing. And it is essentially twice h cross times the energy derivative. Look at the lower right box, 2 times h cross times d delta by dE. It is the energy derivative of the scattering phase shift. Mind you, the important term is the variation of the phase shift with respect to energy, or equivalently with respect to momentum or with respect to k. The physics is the same, only the math is marginally hardly different. H cross is an important term. In atomic units it will go away, does not matter, but the factor 2 is an important one. It is h cross times d by dE of twice delta, okay. And that it is twice delta is because the delay is occurring twice, as the projectile approaches the target and then as the scattered particle moves away. So, that is where the factor of 2 which is coming in, okay. So, it is twice delta, and this is going to be of importance to us in our discussion in the next class, or maybe the one tomorrow. because in photoionization you do not have an incoming wave, you have only the scattered wave. So, the photoionization time delay is not twice h cross d delta by dE, but it is only h cross times d delta by dE, it is half of this. Photoionization is something sometimes regarded as half scattering, and that is where the factor of 2 has to be taken care of. So, I will leave you with these thoughts. This is our overall picture. In photoionization you never had an incident electron which existed. The electron is only born at the after photoionization takes place, it escapes toward the detector, and it actually defines the axis of symmetry, because what is an axis of symmetry in space? You can take any direction and say that okay, this is my z axis, means what is a coordinate system x, y, z, you can rotate this or dance with this mudra any which way, and everything is fine. So, it is the physics which picks up an axis of symmetry. So, in the collision, which is the lower left box, the incident beam, it defines the z axis, okay, and all the angles r and theta, theta is the polar angle which is measured with respect to the polar axis. So, this is the z axis, and angles with respect to this will be your polar angle theta. But in photoionization, the only thing which can define an axis is the photoelectron escape direction, which is what is shown over here. It is this. So, this becomes your z axis. Z axis is now pointing from my elbow to the finger. So, this becomes my z axis, and the polar angles theta are these angles with reference to the polar axis. So, this is important. Photoionization, however, is half scattering. So, the photoionization time delay would be h cross d delta by dE, but then the physics is different. Photoionization, I mentioned from the picture, there is a suggestion that this is a time reversed process, but time reversal symmetry has got a completely different meaning in quantum mechanics. Classical physics is invariant if t goes to minus t. If you look at Newton's equation, it is F equal to mass times d2r by dt2. So, the second order derivative of with respect to time comes. So, if t goes to minus t, the second order derivative remains invariant. It is the same in the Lagrange equation. In the Hamilton's equation you have first order derivative, but the equations for q dot and p dot, there is an asymmetry in sign. So, that takes care of it. Okay. So, the classical equations, whether it is Newton, Lagrange or Hamilton, whatever it is, they are all invariant with respect to t going to minus t. Who told you that the Schrodinger equation is invariant? What happens to the Schrodinger equation when t goes to minus t? It is a bit complicated. So, I will be discussing that. So, that is the time reversal symmetry in quantum mechanics. I think I might come to that in tomorrow's first lecture rather than today's second lecture, because in today's second lecture I want to discuss the Smith version of time delay. What we have discussed is the Eisenbud-Wigner version of time delay. So, in the next class after lunch, again after a light lunch, we will discuss the Smith version of time delay, and that is important for one very major idea that I am going to discuss. Is this time delay measurable? Is it representable by a quantum operator which is self-adjoint, because observables can be represented by self-adjoint operators. If an operator is not self-adjoint, then it does not correspond to an observable. And there is no operator for time in quantum mechanics. I emphasized that yesterday as well. Okay, the uncertainty delta E delta T is not on the same platform as the uncertainty delta Q delta P, because delta Q delta P uncertainty comes from consideration of expectation values and variance, root mean square variance of operators for position and momentum. You cannot do that for energy and time, because the operator for energy is of course the Hamiltonian, but there is no operator for time. And we are going to be talking about time delay, which you are going to measure. So it is important to establish that it is representable by a self adjoint operator, and we are going to do that in the context of the Smith's formulation of time delay, which is well suited to demonstrate that there is a Hermitian operator corresponding to the time delay. So that will be our topic of discussion. So here I already have a result which you would have noticed, that this is the scattering time delay, which has got a factor of 2 in scattering, but when I talk about half scattering for photoionization, this factor of 2 is dropped, and now you see why it is dropped. Okay? So we will pick up the discussion from this point in the next class after lunch. If there is any question, we can certainly discuss, otherwise we can disperse for lunch. Any question?
So, this time delay mentioned between the.
Yeah, you may want to come up to the microphone. Yeah.
Sir, this time delay which you are mentioning between the incident wave and the scattered wave, how do we know that it's different actually from the time, because it takes time to even measure the scattered beam, like this, it takes time for the scattered beam to reach a detector, and there is always a delay there.
Yeah, so it is the interval which is measurable. It is the interval which is measurable. It is like looking at the railway timetable, and you expect the train to reach your railway station at a certain instant of time, and it is with reference to that you talk about either a delay, or you can even talk about a negative delay if it comes sooner than expected, okay, which is technically called as time advancement. And time delay, Wigner time delay, can be both positive or negative, but only with reference to now why is it getting delayed, or why does it arrive sooner than expected? It is because something has happened in between, okay, that is scattering. Okay, so the information about that event is now, it goes as a signature in the time delay. So it is with reference to when you expect the unscattered wave to arrive. It is the time at which you expect a train to arrive if nothing happens in between and it just comes as scheduled. Yeah? Okay.